The next speaker is Professor Gerhard Holzapfel from the Technical University of Graz in Austria. So Professor Holzapfel is a member of the Austrian Academy of Sciences. He is also a member of the European Academies, the one in Salzburg and Academia Europea. He received very prestigious awards in mechanics, particularly this year, in 2022, he received both the Coiter Medal and from the American Society of Mechanical Engineers and the Prager Medal from the Society of Engineering Science. So he gives very often plenary lectures around the world, so I'm very happy to have here Professor Holzapfel.
Thank you. Thank you very much. It's a great pleasure to be here, and before I start, the reason I'm here is Marco Amabile. He invited me here, and also Francesco Dell'Isola. Thank you so much. And I already suggested maybe to change the Department of Architecture here with my department, just to switch over. But then I thought, I'm not sure if the quality of science is going up or down when you are here and working here. But it's certainly a great opportunity to be here and to speak in a theater, which I never did before. So about my topic, I would like to talk about fiber-reinforced biosolids. And most of our organs in our body are fiber-reinforced, and we want to better understand that. What is the interaction, actually, of the microstructure of the tissues we have in our body and the related mechanics? Because several diseases are based on that. I just mentioned the aortic dissection. I mentioned the aneurysm, where it is basically a malformation and a change in the microstructure. And we really want to better understand what's going on there. So this is a general overview. I want to talk about this interaction. I want to describe actually this interaction between the structure and mechanics on an example of arteries. This is a good example for that. And then I want to show you a continuum model approaches where you include basically a non-symmetric fiber dispersion, because these collagen fibers, they are dispersed in our arteries. And I show you also a discrete approach how to do that. And finally, I will talk about a very interesting application. This is an aortic dissection where we do also fracture modeling. Okay, so let me start with fiber-reinforced solids. So you have here the cartilage, and what you can clearly see, the cartilage here, you have collagen structures here in basically 3 layers, and they really change their orientation throughout the cartilage. This is another example. This is an intervertebral disc, and you see here, even with your naked eyes, you have strong collagen fiber. So this is not an isotropic material at all. This is basically a transversal isotropic material where you have strong collagen fibers. Or our myocardium. The myocardium in our heart basically is here embedded between the epicardium and the endocardium. And when you do a second harmonic generation microscopy, you see also fibers embedded in a certain matrix material, and you see the fibers here, and these are endomusial collagen fibers actually going around here. So these are just some examples where we have a fiber reinforcement in a tissue. It's like in civil engineering, you have this steel which reinforces, so to say, the concrete, but here we have the collagen fibers which reinforce the organ, but always undergoing large deformations, large strains. So we cannot use any linear theory here. And that's the right place to be here at the Nonlinear Solid Mechanics Conference, because everything is nonlinear here. When you look in the artery, you have 3 layers, and all these 3 layers are really load-bearing, the intima, media, and the adventitia. And here you see histological sections, and these are different materials. They have different functions, they have a different microstructure. Basically, one layer consists of a couple of components, very similar again to concrete. You also have a couple of components which come together to a composite. Here we have collagen. And you see the collagen in the unloaded state is wavy. That means you have to stretch it up to become straight in order to be load-bearing. Very clearly seen here. So this is the most important component. It is a load-bearing component, collagen. Then we have elastin. This is like a rubber-like material. It's isotropic. You have elastic fibers all over the place. So you have an isotropic material here. Then, in the media, you have smooth muscle cells. So here is a smooth muscle cells. You have activation. That means you have a calcium influx, and based on that, you have a contraction. And due to this contraction, you have a generation of force. So the muscle activation is very important. And then, between these collagen fibers, they're sitting so-called proteoglycans. We are not sure yet the mechanical component of these proteoglycans. These are very tiny structures you see here, and what we know is they keep the water. They keep the water in the tissue, and but the mechanical characteristic for the arteries at least is not that known. So how can we image that? We use a second harmonic imaging microscopy. So a laser light here, what you see here, a laser light is basically generating here a frequency double light, and you can visualize the collagen structure therein and also changes in the collagen structure, like due to certain diseases such as tissue disorders like cancer, etc. Here you see a segment of a human abdominal aorta, but when we use the second harmonic generation, the problem here is you just have a penetration of 120 micrometer, which is very little. So you cannot walk through the wall. So what we are doing here, we clear up this tissue so that you can really literally look through, and when we do the clearing at the end, you have this sample here, and I don't have a sample with me, but you can look through, and then we get a penetration up to 2 millimeters. So for these materials, we can actually visualize the 3-dimensional fiber structure. This is fantastic, of course. So we can model that, we can extract this fiber structure and bring in a solid model. So here is one example. You see, this is the inner wall, and this is the outer wall. So here we are walking through an abdominal aorta, and you see the change in the fiber structure. This is the intima, media, and adventitia. So 3 different materials, and this is another view. So this is a so-called intensity plot. Let me briefly explain what that is. Again, this is the inner wall, and this is the outer wall. This is the thickness of the aorta. This is the innermost layer. This is a kind of transition zone, transition layer. This is the media, the middle layer, and this is the outermost layer. Red means we have detected a fiber, a collagen fiber. Blue means there's no fiber there. So that means here we have isotropy basically, but here 0 means in the circumferential direction we have pretty much collagen fibers here in the media, but here at 90 degrees towards the axial direction we have the collagen fibers in the adventitia. The point is here, we are able now to characterize this spatial orientation of the fiber. Okay, this is a message here. So what we find that in our blood vessels, this fiber structure is basically with these 2 families. This is the circumferential direction. So about plus minus 40 degrees, we have a mean fiber angle, and we have some dispersion, you see. We have these two mountains, so to say. And then we also have out-of-plane dispersion. You know, this is in the radial direction, which is much smaller. And what we observed, that this characteristic dispersion is changing with disease. For example, when you have an aneurysm, this out-of-plane dispersion is increasing. So it's really disturbed the collagen fiber structure. So I show you here, this is a movie where we were able to extract the collagen fibers, which are seen here in green for a stretch up to, I think it was 10%. So you see these collagen fibers are straight. They are not wavy anymore. And these yellow bits, these dots here, these are the proteoglycans binding these collagen fibers together. So this is in the nanoscale. So this is 100 nanometer. So, and we found papers, they actually extracted these proteoglycans and they stretch it up. So you can put on piconewton. This is the level of force what you can put on these proteoglycans. So this is possible these days. That was impossible maybe 10, 15 years ago. So now we want to understand how does a microstructure contribute to the overall mechanics. So we're doing typically these biaxial extension tests, but now we do it under the microscope. And you see here a picture on the microscale, which is in green, again, the collagen fibers, and in orange, the elastic fibers, the elastin. And this is a nanoscale, where I have these fibrils of collagen, and these black dots are the proteoglycans. So when you stretch up this tissue, this is the unloaded state, you see in the unloaded state, it's very wavy. This collagen is really completely disorganized. But then, this is a stress versus a stretch. So it's very weak at the beginning, but then continuously, when we stretch it up, the fibers get straight, and finally, you have this very typical exponential function, exponential stiffening, because these collagen fibers kick in and bear the load. So this we can now understand. We can really study the reorientation and the rearrangement of this tissue based on the loading and based on different loading types. So this is the interaction we really want to better understand. I show you now two continuum model approaches, and one is a non-symmetric fiber dispersion. This is basically also implemented in Abacus. Abacus took that and implemented that. So we have two options. This is the so-called angular integration. I call it AI. So in the angular integration, you have the following. You have N. This is an orientation vector of a collagen fiber. Yeah? You have one collagen fiber here, and this collagen fiber you can describe by two Euler angles. Very simple. This is the formula here. You have the Euler angle phi and theta. Okay? So this is the N here. But this is not just one number, you know. It's not just one direction. You have a kind of distribution here, and I show this in this way. You have a relative angular density of fibers, which we call rho. So you have this angular density as a function of n. Okay? Then you have the normalization condition, and omega is a surface of a unit sphere. So you do this in a unit sphere, and we say W here is the energy stored in a single fiber. Okay? If this energy is, well, if the stretch lambda is smaller than 1, then we have compression, and we assume that this fiber does not bear any load, does not store any energy. That means this is 0. We just exclude that from the unit sphere. And then the N here is the number of fibers per unit reference volume, and this is, again, the strain energy. So this is one approach. The disadvantage is extremely time-consuming, because you have to do the integration over this unit volume, over this unit sphere, and then you have to actually compute the boundary where lambda is equal to 1. And this part where lambda is smaller than 1, you have to neglect. That means this integration is very, very time-consuming. And the second one is a generalized structure tensor. I call it GST, where you have the right Cauchy green tensor and some structure tensor H. And this structure tensor is described in this form, where M is the mean orientation of collagen fibers. Very simple form. And this has the property that the trace of this structure tensor is equal to 1. So this is a second approach which is very efficient, and as I mentioned, this is also implemented in Abacus and several other software codes. So that go back to Nonlinear, 1983, and this Advani published this the very first time in 1987, and then my 2000 model also is based on this general structure tensor. We have shown recently that both approaches have basically the same power to predict something. You know, this is the same. You can fit the same curve basically. It's just a different model, because there was an argument. Well, this model is better than the other, and this model is for this and that reason. It's not the case. So we showed that they are really essentially equivalent for a significant range of large deformations. This we published in the European Journal of Mechanics A solids with Ray Ogden. So now let me briefly explain this model. You see here these two peaks, as I have shown previously, and these are the peaks from above. This is the in-plane dispersion. Here you have the circumferential direction of the aorta, and this is the axial direction. So basically, you have the mean fiber direction I call M, and M is cosine alpha here, cos alpha E1 plus sine alpha. And then we have a density of fibers, rho, in plane and out of plane. So it's very clear that you have here an in plane and an out of plane symmetry. So that means we split up this density in plane and out of plane. So, and for that we use, for this in plane and out of plane, just a von Mises distribution. For both, von Mises distribution with a concentration parameter A and B. And then you can also show the details you find in the paper, but important is the message behind that when you have A and B, you can actually define a dispersion parameter in plane and a dispersion parameter out of plane, which has some bounds here from 0 to 1, for example, for the in plane, and from 0 to a half, here you see this for the out of plane. This comes from imaging. This has nothing to do with mechanics, basically. So the visualization is like that. So you have the density here as a function of n. This is typically a non-rotational symmetric dispersion. Here you have a rotational symmetric dispersion. No dispersion. That means you just have straight fibers. And then you have a 3D isotropic dispersion, so you get the sphere. And here you have a planar dispersion. So in this model you have, as special cases, different types of dispersion arrangements included. As I said, Abacus has really taken that model. But to briefly explain, you have these two families of fiber. That means you not only have an M4, you also have an M6. So this is a second family, the second mean fiber direction, and this dispersion here. And then you have the basic invariance. Everybody knows here, this is basic strength of material. The first invariant is the trace of the right Cauchy-Green tensor. Then you have the I4 and the I6, which is a double contraction of the right Cauchy-Green tensor with a dyadic product of this mean fiber direction. And here we have an additional invariant with Mn. And Mn comes from the cross product between M4 and M6. You see, Mn normal is basically the orthogonal vector to this plane M4 and M6. I don't show the detail, but you can get a generalized structure tensor here, and when you multiply by C with the right Cauchy-Green tensor, and you put in the trace, then you get an invariant, a modified invariant I call I star 4 and 6. So we have two additional invariants, whereby these invariants are functions A and B, and these A and B are just composed of these dispersion parameters, what we got from imaging. So this is very nice, and at the end of the day we have structural parameters. So this is an in-plane dispersion, out-of-plane dispersion, and the mean fiber direction in these two families of fibers. So these four parameters we get from imaging. from second harmonic generation, from polarized light microscopy, using picoserious red staining, etc. So this is, we really extract from imaging. This is basically the steel reinforcement in the concrete, what we describe with that. So how does the mechanics now go? So this is structure. We just take this strain energy function. This is now a function of I1, isotropy, and these two more complicated invariants. So it's invariant based. That's important. Don't use any green Lagrangian strain components here, because you really want to be independent of the coordinate system. So we use invariants. So for the isotropic material, we use just a neo-Hookean material, and for the anisotropic part, we use an exponential function. You have seen this curve going up. It makes sense to do an exponential function, which goes back to Fung. Fung was the first who described in 1967 in a paper that the stiffening of a soft biological tissue follows an exponential function, is K2 times I alpha star, and alpha is 4 and 6. You see, and you have additional parameters here, namely mu, K1, and K2. That's it. That's the mechanics. So you have 3 parameters for the mechanics, and you have 1, 2 dispersion parameters plus the mean direction. Let me do an example. So we have here, this is the outermost layer of an abdominal aorta, human abdominal aorta, and we were cutting out here a piece of tissue in axial direction. You see that here. This is the axial direction, and this is the circumferential direction. And then we did some tests. We just stretched it up, and you see here the Cauchy stress versus the stretch. And what you see here, the blue data is the stiffening in the axial direction, and the red data in the circumferential direction. So what can we learn from that? First, it's highly anisotropic. So it's totally, completely different curves, and it's highly nonlinear solid mechanics. So this is what we can see. And what do you think, why is this much stiffer in the axial direction? Because of the alignment of the collagen fibers. So we have more collagen fibers in the axial direction, which I have shown in one of the previous slides. So this is a function of the microstructure. So what we have done then is we have analyzed the microstructure, and we were able to extract from the imaging these 3 numbers: the in-plane dispersion, the out-of-plane dispersion, and the mean fiber. So this comes from the imaging. And then we have done the fitting based on the mechanical tests, and then we got the mu parameter for the neo-Hookean material, and the K1 and K2 for the exponential function. This comes from the mechanics, completely separated, and when we do the fit, this is a model, gives perfect fit. So this is nice. So we can really visualize now in these days, and that was not 10 years ago, and extract the microstructure and put it in the model. And we have also implemented that in Abacus many years ago. So we have computed here this uniaxial extension. This was in the circumferential direction. It's a stretch 1.3, so 30% of strain. And this is a Cauchy stress in the axial direction. And here, this is in the axial direction. This is circumferential axial. And you see this at 1.3, that you get a different stress level here in this zone in between. And this works quite stable. Let me now do the second part. This is a discrete fiber dispersion approach. Why is it important? Because here, for the continuous approach, it's not so easy to actually switch off when I4 or lambda is smaller than 1. So we thought it would be better to do a discrete fiber dispersion for this reason, to exclude the fibers when they are smaller than 1, because when you have really 2 slanted bars and you put some compression in, they are not able to bear any load. So we have to really get rid of that. And so what we do is we have this unit sphere, and you have this discretization of this density function, probability density function over rho. So, and when we discretize that, so you have a number of elements here, and for each element you describe, so to say, your mean fiber direction. Several advantages I don't want to go through here. Because of symmetry, we just use here 1/2. So we have now the elementary fiber density here, rho n, which is here the double integral of rho times sine theta. We have also the normalization condition, and the elementary fiber density is then evaluated numerically within each spherical triangle. So we now can treat the contribution of all the fibers to the strain energy function in a discrete manner. We just sum from, and we assume how many fibers are in, 10, 20, 100, 1,000, and you will tell me, well, how do I know how many fibers I should take? I will show you later. So then the energy stored in the fibers, it is rho n now, the discretized density, times W, those the energy for one single fiber as a function of lambda squared, and we sum up from 1 to m. Okay? So, and this Wn can then be any function. Could be a linear function, could be an exponential function, but we just say we take that if this is larger than 1, otherwise we just say it's 0. And we have also to satisfy this condition that f at 1 or f prime at 1 is equal to 0. So we have used an exponential function here also. So how to consider now recruitment and damage? You know, the fiber looks like that in the undeformed configuration, and lambda f is 1, but then at a certain time the fiber is straight, and from this condition on, the fiber is bearing load. And this we call fiber recruitment stretch. Let's call it lambda A, fiber recruitment stretch. And then we have the through fiber stretch is then lambda n is lambda f divided by lambda r. And this fiber recruitment stretch actually we can visualize. Of course, it's not a number. This is again a distribution. And finally, we have damage here and rupture. So damage will induce because we overstretch the fiber and finally it ruptures. So that is the idea, to use very simple continuum damage mechanics here, so that we see this sum of rho n Wn is also, yeah, we just multiply here by 1 minus d, and this is basically, well, this is the undamaged matrix material, this is the undamaged collagen fibers, and then we multiply here by this reduction factor for the matrix and the fibers, which basically goes back to Kachanov, this very simple. He published this in 1958, but it works quite nice. So I show you now an example. This is a uniaxial tension experiment of a strip. This is a block what we have, and we have a fiber dispersion here embedded. What you see here, m is a mean fiber direction. Here, m, we have 60 degrees, and this is a dispersion. We have used some dispersion here, and then we stretch it up. You can imagine what happens. This is a very complex problem. It's uniaxial extension, but the mean fiber direction is not along the loading direction. Tricky, because you will induce a lot of shear, and you will induce twist and so forth, and that you see here. So it twists, and this is a stress, the Cauchy stress in the third direction. So it's quite tricky. Again, I show this again. So this is a finite element analysis. There's no closed form solution anymore. Okay, this is a continuous model as I have shown previously. And this is now a choice of m. M we just have used 640. And you see that the match is already relatively good. And when we choose 4,000, it's, I think we are right there. But we reduce, and this is an important point, we reduce the CPU time here from 12,000 seconds to 53 seconds. So the take-home message here is very cheap. This discrete fiber approach is extremely cheap, and you can really compute here large-scale systems with the advantage that you can really get rid of the compressive fibers. And you see here, this is another example. We did an experiment here also on the thoracic aorta. These are the finite element, this is finite element discretization. Then we also extracted the fiber dispersion. They were quantified, and we identified plus minus 19 degrees as a mean fiber direction, and then also a dispersion parameter where B is a concentration parameter there. So we extracted from imaging, and also from imaging we got this fiber recruitment stretch. You know, at which point or at which lambda, stretch lambda, the collagen fiber is really straight, and that varied between here 0.34 and 0.43. So we used also a statistical distribution of this fiber recruitment, and then we just did this analysis. So with a very low stress, we're going up elastically, we go down. This was full elastic, and I show later on, you will see when you go further on, you induce already damage and you generate dissipation here. And finally here we come by the last loading cycle, we go up and that ruptures finally because of severe damage. You see that here. And this you see clearly in this plot. This is a Cauchy stress versus stretch. This is experiment. So very soft at the beginning because the matrix material is basically load-bearing, and then after some points the collagen fibers kick in. It's very stiff, and then you see some softening behavior, damage, and finally you have rupture. This is experiment we did, and this is a first loading cycle, so it's a very good fit. This is a second loading cycle where you already see a dissipation here. So you have some damage, and finally this is a third loading where we have finally the rupture. So when you don't do the damage, then you have a purely elastic curve where you never get the softening, which makes sense. So that works quite well. And you see that also here in this finite element analysis, we have very high stress concentrations here, and this you see in the experiment, the rupture is really at this location. So that was very nice to see the comparison with the experiment. So finally, how many minutes do I have? 10 minutes?
You have 10.
10? That's fine. This is a very interesting topic, aortic dissection. So we have a very big project, and Marco knows exactly, about 10 PhD students are involved here in Graz, where we want to better understand why does an aorta rupture suddenly in the ascending aorta and descending aorta. And this is, according to Professor Bachand, I mean, this is material science. This is really a rupture of a material. So this has not much to do with medicine. So this is something we as engineers and mechanicians have to look at. And I show you the problem first. So this is typically a type A dissection. So here you have the heart. And the type A dissection means you have a rupture here, just at between the valves and the arch here. This is Stanford type A, it's called. And this is very dangerous because when you have a dissection here, you most probably need a helicopter to do the surgery, otherwise it's too late. In many cases, also interesting, this dissection is combined with an aneurysm. An aneurysm is a dilatation of the aorta. So that might happen that you have first an aneurysm and finally you have a kind of dissection there. The tricky thing is that happens asymptomatic. The patient doesn't feel anything. It happens suddenly. And it's of course very dangerous. I show you here an in vivo movie, which is done by my friend at Stanford from a 45-year-old man. And before I show the movie, I explain briefly. This is the heart. This is the valve. And you see here this abdominal aorta, which is this branch here going up to the arch. But as you can see, this is much bigger than normal. So it's an aneurysm. It's already an aneurysm. And at that location, here, the crack occurred. This is an aortic dissection. And you can imagine when during the cardiac cycle, when the pump when the blood is flowing, then you have a kind of dynamic response of this flap. And these are the ribs, what you see here. So I show you this movie. It's very impressive. So let me. So you see this flap here moving in the bloodstream. And here you see the coronary arteries. So, and this was really tissue failure, basically. And this basically fails, and the crack occurs, of course, in the intima, in the innermost layer, and then it goes to the middle layer, and then it propagates down within the middle layer. It's seldom the case that it just ruptures. But the crack propagates in the middle layer, and this is a terrible disease. So this is a problem to model, to better understand why does it happen, how can we treat it, how can we predict something here on that, how can we design stent grafts, because these guys, they have surgery and you put in a stent graft, how can we optimize that based on a certain morphology? So this is a very interesting engineering problem. So I briefly mentioned, and I have a couple of more minutes, to how do we model that? And we use a phase field approach. This is one possibility. So we have here the primary variables, basically the deformation map, lowercase x is a function of uppercase x, and the crack phase field D, which goes between 0 and 1. 0 is the intact state and 1 is a ruptured state. And in 1D, you see here the field equation for the crack phase field. When you have a bar here and you have a crack, that would mean here you have 1 because you have the crack here, and everywhere else you have 0. Okay? So at x equal to 0, you have 1, otherwise you have 0. But this is numerically impossible. This is a singularity. You can't implement that. So that means you smear that out, basically. You approximate that, and you do a kind of diffusive crack. That's what you see here in green. This is, so we use just an exponential function of minus x over L. L is a length parameter. So if this length parameter goes to 0, then you have this singularity, but numerically this cannot be done. So the question is, of course, how big is this L? So this is a user-defined parameter which has no physical meaning. This is just a numerical parameter. So this is a basic idea of the phase field approach what we used here. So we used this equation again, what I have just shown you, the isotropic strain energy function, the anisotropic strain energy function, and then here we multiply this psi 0 by this with this g, and this g is a type of degradation function. This degradation function we just use here 1 minus d squared, where we have a certain growth condition, g prime is smaller or equal to 0, and then we have these limits for intact or ruptured state, 1 or 0, and then here we ensure the saturation of g when d goes to 1, basically, so g prime has to be 0. So this is a relatively standard concept, and what we can derive is the first Bühler-Kirchhoff stress, very basic. So this is a strain energy function with respect to the deformation gradient, and I call it the energetic force F, which is minus the derivative of the strain energy function with respect to this, this parameter d. Okay? And then we have to do our homework. We have to set up the power balance laws, which consists here not only of the rate of energy storage, external power, but also on the crack dissipation. So you have to, of course, add that. And then you need a mixed variation principle. and you get two Euler-Lagrange equations. Now in short, this is very famous. This is the equilibrium equation as a function of just the first Euler-Kirchhoff stress here. And this equation where F, this is the energetic forces again, minus Gc, this is a critical fracture energy, and this is a variational derivative of the crack surface, which was published by me here a couple of times, was it 10 years ago. Then we have the unloading loading conditions, which people know in computational mechanics. And we use, and there's no time to talk about this, an energy-based anisotropic failure criterion, energy-based. This turned out to be the best criterion we can use. Now finally I show you an example. So this is an abdominal aortic aneurysm which we have gotten, and then we have taken a simple shear test. So we have cut out basically a block, and you might see that here this block is here glued on a plate, and here we have cut into this block a small slice here, because we want to initiate the crack in this cut. And here you see the test. This is basically the tissue here, and we shear this upper part against this lower part within a liquid of 37 degrees. And this you see here. Now there's a small cut in, and when we shear that, we get a fracture. What you see here, at the end of the day, you have two pieces in hand. This is fantastic. We call in continuum mechanics this is simple shear, but I always say a simple shear is really not simple. This is a very complicated mode to analyze. I show that again. And of course, this we need because we have this mode also in our body. So you see, this here starts the crack, and we measure, of course, the shear force versus the amount of shear. Why do we have shear in our body? Maybe not in the abdomen, but the heart have a torsion of about 10 degrees in vivo. And this torsion, of course, is transferred into shear. And this shear is, of course, mixed with normal stresses, but the shear is an important mode, in particular when the rupture occurs in the ascending aorta. So here are the results. The in-plane shear, you just load it up here to 150 kilopascal, almost linear, and then you have the rupture and it goes down. So this is based on about 10 samples. It looks very similar. Of course you have some deviations, much more as in technical materials like steel or concrete, but you get a picture. And this was also interesting. This was out of plane shear. You see here we have 1,500, and this is 150. That means the strength there is 10 times higher. So we didn't know first. That means for the rupture, just forget this plane, because it's very, very strong here. And what we have modeled is this curve now. So we have just discretized this simple shear test with these two notches, about 23,000 tetrahedral elements. And then we have applied the loads. This is experiment again. And you see here the crack phase, the evolution of the crack phase field. And this is evolution of the shear stress. And here you see that we just get the same numbers basically as the experiment. But that's why I say it's not simple, the simple shear. You see, it's a highly complicated three-dimensional stress pattern here, what you can see. So I want to stop here already. The summary is really that we are now at the right time to do more patient-specific analysis. We have the imaging technology. We have CPU times. We can really do very fast computation. That was not the case previously. And there is a great interest from the medical side they ask us, why is that the case, and which stand or standcraft are we using here, or should we use here? So they base everything on the statistics, but they don't understand really the mechanism. So it's a right time to go towards this direction. I want to thank really a couple of postdocs here. Michele Tazzano is sitting here in the auditorium, a couple of graduate students, and also a lot of collaborators. One is sitting here on my side, Marco, the first place, and well, many are here just in biomechanics. Well, Ray Ogden, he's well known in general mechanics. And a couple of funding I really want to thank. I was proud to could contribute to 2 NIH projects as someone sitting in Europe, which was very nice, which was also on biomechanics. So with that, I want to thank you very much for your attention, and I'm happy to take any questions. Thank you.
So we have a question from Bergen Gayesh.
Microphone.
I think they are coming.
Thank you, Professor Holzapfel, for the great talk. I'm Melvin, assistant professor with the University of Adelaide from Australia, long distance. I have 3 PhD students working in the same field, but we concentrate mainly on the fluid structure interaction of the aortic system. And we use your data. I remember some of the papers that we got stress-strain relations. And what we do, we take those data, we implement them into our simulations for fluid vibration. And from the vibration of aortic walls, we extract some information for the prediction of dissection, plug rupture, and crack propagation. From your talk and from your papers, I can understand that it's a very complicated topic with many parameters involved in the analysis. For someone like me or my research group that we want to use the data from your work, I was wondering that if there is any simplifications or simplifications which are to some extent reliable, because if I want to implement all of these complexities in my dynamical analysis, it takes ages to run the simulations. And we have to make, for example, for the artery wall, we assume that it has 3 layers, and for each layer, in our simulations, we use as orthotropic material, roughly. But if I want to go further for anisotropy, for example, then the dimension of the problem becomes very big. So my question is that, is there any simplification that we can make this complicated problem simpler for the second use, but at the same time reliable? Thank you very much.
That's a good point. We are all engineers, and we have to understand what is a main contribution to that what I want to model. If you model everything, what mathematicians want sometimes to do, then you are lost. So we have to figure out what is the effect I really want to understand. And I think for the wall, it's important to model it as nonlinear, because still people are doing a Hookean material, which is not possible, and do it anisotropic. If there are dispersion in or not, this is maybe a detail. This is maybe not important. Take my 2000 model, for example, that's enough. So that's a first attempt, and that's it. And then you have to think about some fracture criterion. You talk to Professor Bashanta, that's the best. Use some damage or some fracture, that's it. When you want to do fluid structure action, then you add a lot of complexity. Then you also have to think about, do you want to do a Newtonian or a non-Newtonian fluid, And then, of course, comes a big problem. When you do it patient-specific, then you have a big system. But this is a way, I think, to go. Don't add too much complexity at the beginning, otherwise you have so many parameters and you can get out everything you like. Just screw at these parameters, and that's not the way how you should do it.
Yeah, thank you very much for your point. We use non-Newtonian and nonlinear and hyperplastic for sure, but still the problem becomes like...
Yeah.
Thank you for the comment.
So I will ask, because I want to make that model more complicated.
Okay.
But in that approach, we would forget a couple of very important effects, which are residual stresses and viscoelasticity.
Yeah, for example, yeah.
So what?
Yeah. I mean, the residual stress is a point, you know. If you don't have it included, so your stress prediction is probably
Off.
wrong. So you have to come up with some hypotheses, probably, to maybe include it with some rough estimation. I think without residual stresses, you get stress gradients in your arteries which you will never see in vivo. So this is an open issue. What are the residual stresses in our vessels? That's a good point, Marco.
A question from the audience?
Yeah, thanks a lot for the crystal clear lecture. So just a really basic question for my understanding. In the really beginning, you have shown like elastine, gelatin, and many different stuff. What is in between? I mean, is this like a composite material embedded in a matrix in our body? Do we know what is that, or is this just void?
No, this is a composite material, per definition. You have fibers which are embedded in this matrix material. Now the question comes, what is the interaction between these collagen fibers and the matrix material? The answer is, we don't know. We don't know this law of this interaction. And then also the smooth muscle cells are embedded, and this microstructure is very well known. It's a composite. You can think of as a composite. But to find out the microstructure and the interaction, this is an open issue. We could work on that. I'm thinking of many years about what is the interaction of these collagen fibers and the matrix material. And this is important when you talk about rupture.
I have a question to the strain energy function.
Yes?
Could you give your slide with the strain energy function of I1 plus I star, 2 I stars?
So, well...
Just one of them, you have 2 slides.
Well, here I think I showed that. Here, this one?
Yeah, this one.
Yes, okay.
If you write the strain energy function like that, you have 3 parameters, and you have to say something about principal directions. Are the principal directions the same?
Well, I1, I think this is very clear, right? This is
very clear.
Very clear.
If you want to get a stress, you have to take a derivative.
Sure.
You took then the derivative to
You see
the
this?
deformation gradient.
Yeah. So this I4 star is here. This is explicit form. I think I even showed that here. This is the I4 star. This is I4 star here. And I6 star. This is the expression here. As a function of the invariants I1, I4, I6, and In. When you derive it with respect to whatever, green Lagrange strain or right Cauchy green tensor, you have to derive this function. It's in the paper, explicitly. And this you need, and you not only need it for the stress, you need to another derivative for the elasticity tensor, because you want...
My point is different. If you speak of symmetric tensors, stress and strain,
Yes?
you have 6 components.
Yes?
And you can take these 6 components as 3 principal directions being the same for stress and strain, but then it's isotropy.
Okay.
And then you have 3 invariants. You can take whatever you want, but these are scalars. And what you said, the second summoned is anisotropic.
This is
I
anisotropic.
think.
Yeah.
Well, this is a scalar equation. Sorry.
This is a yes, this is an invariant. This is a modified invariant.
Yeah.
Correct, yeah. I showed this. You see?
Okay.
Okay, I have one question here. Saeed Aziz from the University of Strasbourg. I would like to know what finite element code did you use? Second, these rubber elasticity models that you have applied or developed, are they existing in these codes or you had to implement them?
Well, in terms of finite element, we have used a mixed formulation because we have the incompressibility here, J equal to 1, so we use an augmented Lagrangian iteration in order to constrain J equal to 1. When you use a normal Galerkin principle, a displacement-based finite element, that will not work because it will lock. So we used a mixed formulation. This is the first answer. So Q1P0, I don't know if you...
Which code did you use?
Well, we used FEEP for the development, FEEP, but we have implemented this also in Abacus, and this is also a mixed element what we have chosen there. So it's a UMAT code what we wrote basically. But this you can take from Abacus basically, without doing anything.
Okay, thank you.
But you need a mixed formulation.
I've seen Professor Plachely before with the raised hand. It will be the last question, please.
I would like to know if there is some relation between the form of W of lambda in slide number 9 and the constitutive parameters K1, K2, and mu that you have used for psi analysis.
The relationship between these parameters
psi
and
of lambda, where in slide number 9, when you have the relation between here W psi f, that is an integral overall orientation,
right,
weighted by the
W
function
of
W of lambda. Is it possible? We have developed in granular micromechanics. It is possible to develop a relation between the form of W and the form of psi anisotrope that you show in slide number 16. What is the relation?
we haven't investigated that, but this is the angular integration approach. We don't have the K1, K2, and mu here. No, we have that here in this model. In this model, we use the K. No. These are different models.
Okay.
These are different models. And in this one paper, what I have pointed out here in this paper, we have shown that these are different models, but they are essentially doing the same thing.
Yeah. In fact, granular micromechanics can be related. So this is a common.
This we tried actually. We did not succeed. So this you cannot relate. We cannot relate one parameter from one model to the other parameter from the other model. This we didn't succeed on that.
Maybe we can discuss.
Yeah.
So, thank you again.
Thank you.